Hello, everybody. My name is Sualp Ozel, and I am the product manager for Autodesk Simulation Mechanical. Today with me, I have Nelson Vu, who's the support manager for MotionPort, focused on dynamic simulation offerings from a software called Recurdyn. So we will focus today's webinar on interoperability between simulation mechanical and Recurdyn to solve some complex dynamic simulation problems. So let's get started. Before we dive into today's topic, I have a couple of important announcements around simulation mechanical. So the first one is that our Service Pack 1 for the 2016 release is live on the knowledge.autodesk.com webpage. You will have to go to that webpage and download the service pack, and then you can install it on top of your 2016 application. And this service pack addresses 30 plus different issues that we have identified with the software, thanks to your continuous feedback. The next announcement is our App Store and its existence, really. We've had a link to the App Store in Simulation Mechanical and CFD and Moldflow for the past several releases, but I just wanted to highlight it one more time. We have a button on the top right corner of Simulation Mechanical with the icon that looks like a X for Autodesk Exchange Apps. And if you click on that, you will land on the landing page that has all the different free apps that we have for all the different simulation products. So for Simulation Mechanical 2016, the one app I recommend is the supplemental results for SimMech 2016. If you have some time while you're downloading the service pack, go ahead and download this one as well. And after you install the service pack, you can install the app that will enable you to take a look at different types of results and do some additional data gathering with Simulation Mechanical. The next topic I want to discuss is around meshing before going into the Recurdyn interoperability. So at this point, I'm going to ask some of my organizers to help me with a quick question. I'm not sure if what will happen on the GoTo meeting screen.
Hi, Sualp. I'm just going to post a poll question here. If everybody would like to go ahead and respond to this, it's: did you know that you can mesh and remesh selected parts in an assembly in 2016? We'll let everybody go through and give it a few more seconds. Looks like just about everybody has responded, waiting for some last-minute votes. All right, we'll go ahead and close this now. And it looks like about 85% of you voted, and 53% are not aware of this functionality. So it's great that Sualp's going to be covering this today.
Excellent, thanks. So this was a question, and I forget exactly where it came from, but it was either on the Idea Station or the user forum. So I figured I'll go ahead and explain this functionality with a quick demonstration. So here I have a 7-part assembly that I have imported from, I believe, a step file. The source really doesn't matter. So what I will do is I will create a first pass mesh on this assembly. When I hit Generate Mesh, it will create the surface mesh using the default settings. And in an ideal world, I could just simply take this very first mesh and start adding loads and boundary conditions and start analyzing my model. But then let's go ahead and add some material so that these red icons go away. So I'll go ahead and add a default material of steel. Okay. So like I said, if everything worked on the first time, or if I was happy with the mesh results and how the mesh looked like, I could be setting up my analysis with some loads and boundary conditions and run the analysis. But um, typically, what I end up doing is I end up needing to remesh one part or maybe a couple of parts in an assembly like this one more time, or maybe a couple more times. And historically, in the 2015 release or before, I would have to pick those parts. So let's go ahead and show you how to do that quickly. I'd pick that part, and let's say that part and that part. And let's say I want to mesh them using a finer mesh size. I would go ahead and say CAD mesh options, use the part-based mesh settings, and I would say use a finer mesh for those guys. Now, when I do that and hit OK, what will happen is if I go to Mesh and if I say Generate 3D Mesh, the software, the 2015 version and the 2016 version, will remesh the entire assembly, even the parts that you don't actually want to remesh. It will mesh everything. And if you have a, for example, 100-part assembly, this process takes a very long time, because now you're remeshing the parts that you don't necessarily want to remesh. You were okay with how they meshed in the first place. And this is the functionality we're talking about, is to be able to remesh certain parts but not the entire assembly. And how do I do that? So what I'll do is I'll start over and say delete CAD mesh and delete all the mesh on all the parts. And I'll go back to my original mesh sizing. And I can either do it manually like this, or I can just say mesh, all parts use model mesh settings, which is another great trick. And this takes me back to the default settings for everything. And I'll create the original mesh that I got with the first pass mesh. And now, let's say I just want to mesh one part by itself. So let's say I just want to part number 4. What I can do in 2016 is I can right-click and say, suppress unselected parts. And that suppresses everything. And then I can say, I just want to change the mesh size for that part to a very fine mesh. Okay. So now that part has a appropriate 3-element through the thickness mesh. And to continue with setting up the analysis, all I have to do is select the parts heading, right-click, and say unsuppress all the parts. And now I basically have only meshed that part. Everything else I didn't remesh, but I'm good to go in terms of setting up this analysis for loads and boundary conditions. Now, the one thing that I have to remember is, of course, now I have an unmatched mesh between the yellow part and the blue part, as well as the red part and the blue part. So what that means is I have to make sure that I set up the contact between these two parts that would consider them to be in either bonded or welded contact. And to do that in the 2016 release, I just have to simply turn on what we call smart bonding. And that's under Setup Parameters. Go to Contact and say, I want to make sure that the fine is bonded to a coarse, or coarse bonded to a fine mesh. And by enabling that and hitting OK, now these two parts will be considered in bonded contact using the smart bonding technique. And that's it. I can continue adding loads and boundary conditions and finally analyze this assembly, and it will analyze with those settings and with those mesh sizes. So this is a pretty nifty method for meshing complex assemblies and then remeshing individual parts or group of parts by suppressing everything else. I hope this was beneficial. So now we are done with the first quick demo. We will move on to the second part, which is our Recurdyn Interoperability. And before we start this one, I also want to take a moment and have you guys answer a quick question.
Thanks, Sualp. That was really great information. We have a question here for everybody. Do you have any need for dynamic simulation in your design process? Feel free to go ahead and select yes or no. We'll leave this open for a few more seconds while everybody's voting, and then we'll give some results to this.
And while we're waiting on some of these results, are there any questions on the meshing technique I used, or any comments on the usability of the ability to mesh or remesh selected parts in an analysis? Is that something that will be useful in your workflow? For those of you who didn't know that, do you think that will be beneficial? And for those of you who knew about that functionality, is that something you're already using? If we can get some comments in the chat, I'd be happy to answer if there are any questions on that. Or if there are any other topics similar to that that you would like to see in future webinars, feel free to let us know.
Sounds good. Looks like we have one person posted, I misunderstood the question. That was useful to learn. Thanks. So it looks like good feedback.
Good.
All right, we'll go ahead and close the poll. I think everybody has voted that's going to, and overwhelmingly it looks like there is a need for the dynamic simulation. So roughly 90% said yes.
Oh, excellent. Okay. All right, so this demonstration will be hopefully very useful for you guys. So in this demo, what I have prepared is a model that is in our tutorial data set. So if you are interested in trying this out on your own, all you have to do is go to our online help documentation, click on the tutorials subsection, and this one I'm about to demonstrate is the one named Piston Mechanical Event Simulation. And I'm doing the part that is in the analyzing and evaluating, but of course if you're starting from scratch, you may want to start with the meshing version of that exact same tutorial. So this is the meshing version where you import a CAD file and start meshing and adding loads and boundary conditions, and then the analyzing section of that same one walks you through some of the information related to adding some different element types, beams and trusses and materials and things like that. So I'm going to start my demonstration with the archive that has all the loads and boundary conditions, if I'm not mistaken. And if I am, that's okay. Let's see. This is in my tutorials folder. Let me open that quickly. So I'm opening the tutorials folder on my other screen, so you're probably not seeing it. Okay, so here is that same model that we were looking at on our tutorial screen. And it's a 5-part assembly, and it utilizes our joint creation utility to connect the parts together. So here looks like we have not only created a solid mesh for the first 3 parts, so that's part 1, part 2, and part 3, but we've also added a couple of joints using the joint creator, which is under the mesh tool. And we did that to connect parts that are not touching each other, and between these 2 parts, and then over here we did the same thing. We created those joints, and then on the back end we also added a joint to this final hole in the model using the joint creator to be able to select, for example, the center points of this pin joint to be able to add prescribed displacements or prescribed rotations to assign the necessary loads to have this piston move in the positive and negative direction of Y. So now that we took a look at the setup, let's take a look at the results. So I'm opening the results archive, and all of this, once again, is already in the tutorials. So I'm not going to actually go over doing the tutorial. What I want to show you is the end product of an analysis like this, which is an MES analysis type, which is in our nonlinear MES. And the couple things I want to highlight is the fact that an analysis like this on our machines take about 15 plus minutes to solve, as we can look at it, as we can see from the log file. And before taking a look at the results, I want to show you the analysis, which is a 1-second analysis with 36 potential results. And the results give us an insight into the full range of motion with all those joints manually created over 36 time steps. Right? And the things we can see in an analysis like this, if you set up an MES analysis, is things like displacement, stress, and strain. Right? This is one way of analyzing an assembly in motion, and this way is certainly a valid method. However, as you can see, we kind of have a very relatively small model of 3 parts and a couple of added joints for a total element count of, and let's take a quick look, total element count of 7,000 elements for the entire assembly. And running an MES analysis like this takes roughly 15 minutes without even considering things like surface-to-surface contact or any other nonlinearity, which would definitely make the analysis longer. Another alternative that you have whenever you're trying to analyze systems like this and are interested in looking at the stress and deformation results within single parts in an assembly while the while the assembly is in motion, is doing an interoperability workflow with a multi-body dynamics simulation tool, such as Recurdyn. So to do that, you would have to do the following. So you would first have to change your analysis type to a natural frequency modal analysis, which creates a new design scenario. And in this new design scenario, we're actually not interested in, let's go ahead and select different selection style. We're not interested in the piston or the crank. We're going to go ahead and suppress them. We're only interested in what's happening to this connecting rod. So if that was the case, if you were only interested in a single part, we can do this analysis so much faster. So what I'll do is I'll go ahead and suppress these other joints as well, and delete the joint meshes that were created. We don't need them anymore. I'll create some new set of joints. So the first thing I'll do is I'll go to Mesh and create a joint on this hole by itself using the universal joint system. Give it a new part number, part 6. And I'll create one more by clicking the Do Not Dismiss button. And I'll select the secondary one, which will be a part 7. And it will also be a universal joint. And when I hit OK, I have now two new joints created in my system. And these 2 joints I'm creating because those center locations are meant to be the connection locations between this part and the piston and the crank parts. So I'll go ahead and select those 2 points in space and add nodal constraints and say those 2 locations are, let's say they're fixed. And the element type for those connections will be rigid elements. So we'll go ahead and choose rigid for that part as well as this part. And we'll accept the standard high stiffness element definition for both rigids. So at this point, we're almost ready to solve this analysis and get the mode shapes out of a natural frequency modal analysis. What I'll do is I'll get into the parameters and take a look at how many modes I'm requesting. Let's say I want the first 10 modes. And then let's also say that I want to output not only the mold shapes, but I want to output the normalized stress and normalized strain information. Now this is really important because we will then reuse some of these files while we're doing our interoperability with Recurdyn. By clicking OK, I can go ahead and run this simulation and take a look at the first 10 mold shapes of any structure. So this we're running this live, but you can kind of see that it's already finished in less than a minute. And we get the first 10 or 100 mold shapes, and we can take a look to understand what the mold shapes look like and what those frequencies are. So once we're satisfied with the results, and maybe we do a couple of mesh refinements to see if the mold shapes are affected by different mesh sizes, we are ready to export this directly into a Recurdyn file called RFI. And what I'll do is I'll just create a 123 RFI file and save it. Once we have the RFI file, we will then reuse this in the Recurdyn software. And to do that part of the demonstration, I will pass the presenter baton to Nelson. And I'll actually ask one of the organizers of the meeting to help me out with this. So let's see. Hi guys, Caitlin or Dean, could you guys help make Nelson the presenter?
Yeah,
okay, I think I just did.
Yeah. Can everybody see my screen?
Yep.
Oh, okay. Hi everybody. As Sualp mentioned, my name is Nelson Wu. I am the support manager for MotionPort, and MotionPort is the master distributor for Recurdyn in the Americas. And Recurdyn is a multi-body dynamic simulation software. So to start out, to continue the process that's of simulating the model here, we would just come into Recurdyn and create a new model and choose unit system. Click OK. And then what we could do is then go and import the geometry for that particular model. It's a step file. And so there's the geometry after I've imported it. And I'm just going to change this, what's called the working plane, which will help me create the revolute joints in the next step. So what I'll do next is start to connect everything together with various types of mechanical joints. So right now I've selected the revolute joint, and I'll pick my base body as ground, and then I'll select this first body as the action body for the joint. And then I'm going to just go ahead and select a point for the location. And I'm going to go ahead and adjust the icon size here so things are easier to see. And I'm going to go ahead and repeat this step. And so basically I'm able to select features of the geometry to help me locate the point correctly. And I'm creating another revolute joint between body 11 and then the piston itself. So I've got Revolute joints, and then I'm going to create a translational joint between ground and the piston. And then I just select this vertical direction there. Now, what I'm going to want to do here is to relocate these joints so that they match up with the master node of the rigid element that was created in the mesh. So what I can do is just open the properties for that joint, and then right now I'm just going to key in, because I know beforehand, what x coordinate I want. So I can just go ahead and move that joint. Things are running a little bit more slowly than usual on my computer because I'm actually running another pretty complex simulation in the background. So usually all these operations are pretty quick. And an alternative way for moving things into place is also you can just select any of the entities that you want to move, and so I'm selecting the markers for that joint, and then I can just click on this basic object control. Oh, there it is. And so this value is, oh, actually, sorry, I think I'm just going to open the properties for this and just use the same method that I did before. So everything looks set up correctly here. And then I'm just gonna, oh, let's see, oh, sorry. What I'll need to do then is, next is to assign the motion to one of these joints. And basically, you can just define any expression to control the motion. So I'm going to have this rotate a full 360 degrees, or 2 times pi radians, and I'm gonna have it go through that motion over a course of 1 second. And now I'm ready to simulate the rigid body model. So I'll go ahead and save this as simple piston demo. And then I'll come to the analysis toolbar, choose the dynamic kinematic analysis option. I'm going to adjust the end time and the number of animation frames that are generated. Click simulate. And so basically, as you can see, the simulation took 0.1 seconds because this is a pretty simple model. And just playing back the animation results, you can see the motion that the model goes through. So now that I've got the model set up, I can go ahead and import the flexible body. So we'll come up to this, let's see, the RFlex toolbar here, and we'll select Import RFI. and then we'll just choose the rigid body that we want to replace with the mesh. So we'll choose that body, body 11. And then we'll go and select the RFI file that was exported from Autodesk. And just click OK. And so you can see that the mesh has been successfully imported. And I just replaced that rigid body. And then if we zoom in here and orient the view, so the connections have been retained. So everything that used to be connected to the rigid body, like this rigid replica joint, is now connected to the flexible body, and the joint location is centered on that master node of the rigid element. So at this point, we're ready to simulate the model. I'm just going to save this as a different model name. Oh, actually, I forgot. Yes, before we simulate the model, we can open up the properties of the RFI flexible body. And so right now, this is displaying a list of the different modes and frequencies. And so we want to only select the modes that we're concerned with. So we're going to get rid of these rigid body modes. So first we'll just unselect everything. And then, since we know that the first six
just to clarify before we go any further. Hello?
Yes.
Oh, hi, this is Sualp. Yeah,
oh,
so
yes.
Just to clarify to everybody, when I gave this RFI file, or when I made this original RFI file I gave to Nelson, I actually did not assign fixed boundary conditions on the edge. So that's why the first 6 modes results that you see are near 0. Those are the free body modes of any object being 0 in the translations in the 3 dimensions and the rotations in 3 dimensions as well. So it looks like I had a little hiccup in my setup. I actually meant to assign no loads or boundary conditions to my model analysis. But as you can see, the 7th mode, which gives us a frequency of 692, is very similar to the first mode that I showed in my analysis. I mean, close enough, obviously, because in my case I did have a boundary condition. Yep, that's the first mode.
Yeah. So one thing about this dialog box is that you're able to, as you select the different modes, you're able to play them and just to
as imported. Yeah, those are the as imported modes and results from Simulation Mechanical.
Yes. Yes.
Yep.
So that, for example, this last mode here that we're going to select is a twisting mode. So we'll select the modes that we want and click OK. And just go ahead and simulate the model.
So just to remind everybody, this analysis, while we were analyzing all 3 parts, took about roughly 15 minutes on Simulation Mechanical because we were doing a full finite element analysis on all the elements or all the time steps. But as you can see, it only takes about 25 seconds when we consider the green part and the orange part as rigid body parts, and only the meshed part as the potential flexible body. In a dynamic simulation package, the ability to run these types of analysis very quickly is the huge benefits we see in interoperability workflows between the two packages.
Yes. So once the simulation is finished, just play back the results, which appear as expected. And then, of course, since this is a flexible body, we can generate contour plots. And we can just calculate the maximum value that it sees throughout the simulation. Right now, we're going to display von Mises stress. Click the OK button, and go ahead and play the animation. I'll just go ahead and play that animation again.
And then, Nelson, could you also talk a little bit about the different types of outputs we can get out of a multi-body dynamics tool? Things like velocity plots or acceleration plots at different points and different locations.
Yeah, right. So, for example, one thing we could do is, let's see if we want to turn on the, we can turn on the display of the force. Let's see if that works. Okay. So yeah, one way is that, we can visualize the force results. And so this is interesting. If we, we can just, actually we could do the same thing for all the joints. Oh, looks like I need to rerun that analysis. Well, anyhow, yeah, I'll go ahead and rerun that.
It almost looks like the creation of the animation file, it takes longer than solving the analysis here.
Yes, yeah, for this particular model, yeah.
Yeah.
And usually this actually doesn't take so long. I've actually got a pretty heavy-duty simulation running in the background, so my whole computer is sort of slowing down today. So if we play those results, you can visualize the forces at the joints. And then the other thing is that you can then plot the results. So if you go to the plotting environment, you can take a look at basically here are all the bodies, and then for each body you can plot the position of the center of mass of each of the body. You can also plot velocities as well, and accelerations, and so there's translational and rotational position, velocity, and acceleration.
That's great.
And then for joints, you can also, for example, for this revolute joint, we can plot the position. So this one is that the first one that is driven through a motion of 360 degrees. So you can see here it ends at 360. We can also plot velocity and acceleration. The other things that can be important to plot are the reaction forces. So those are the reaction forces at that joint. And then for this particular joint that's driving the whole assembly, there's going to be you can plot the driving torque required to drive the model through that motion.
Yep, and this would give you an idea of how powerful of a motor you have to.
Yes.
You have to have that's driving this. Okay.
Yep.
Thank you. Those were all the questions I had prepared for you.
Okay, great. Yeah, I think that's pretty much all I had to present.
Hey, Dean and Caitlin, are there any questions coming in from the chat window?
No,
I think at this point,
questions right now.
Yeah, I think at this point we're about done with our presentation for this interoperability workflow.
Sounds good. We'll leave the lines open for a few minutes and see if anyone has any pressing questions, and then I think we'll go ahead and wrap it up for today. And it looks like we have one here. How dependent is the final solution on the number of modes selected? And that one comes in from Chris.
So, yeah, I guess as you include more modes, your solution is more accurate. So, yeah, usually we recommend sort of including a decent number of the reverse modes that are generated.
Sounds good. Go ahead and, he says, the more the better, thanks.
Yes.
All right.
And one thing that, you can do is to do a study of, you can run several simulations where you're including more and more nodes and then compare your results. And as the results begin to converge, then that gives you a better idea of, for that particular model, how many modes you need to include.
Okay, thanks, Nelson. That's a great tip. All right, feel free to post any other questions. Not getting anything in. Oh, we have one more. How is this different from Inventor dynamic simulation? Can you highlight some of the differences or advantages that this would have?
I'll jump in on that one since Nelson is with Motion Bay. The main difference that we wanted to show in I said Motion Bay. I apologize. MotionPort. It's Function Bay is the name of the company that makes Recurdyn. The main thing we wanted to highlight in this demonstration was a workflow that is only possible if you have Recurdyn and Simulation Mechanical. So as you noticed, what we started with in Simulation Mechanical was the modal analysis and created the mode shapes and the frequencies, and we exported that to Recurdyn. And in Recurdyn, we did the entire dynamic simulation, and the output was the stress and deformation on a given part throughout its motion cycle. Right? So this is a complete different workflow and outcome if you use Inventor's dynamic simulation and Inventor's FEA functionality. So in Inventor's Dynamic Sim and FEA, when you use them together, the workflow is such that you start in dynamic simulation. You run the entire dynamic simulation only considering everything as rigid bodies. And then you take the forces and moments applied to a single part at a single time step and analyze that single time step as a finite element analysis model in static stress by only considering that time step's effects. So the output is stresses and deformations at a single time step, which is very different than what we showed here, which is the stresses and deformations over the entire motion. I hope that clarifies it from the workflow we were highlighting. And of course, in terms of the dynamic simulation capabilities of rigid bodies, there are some differences, but I'm not going to highlight those in this webinar.
Perfect. I think that answered his question perfectly.
I guess if I can add one more comment about that, with the ability to have a flexible part in the model, if the flexibility influences the motion of the overall assembly, that's another advantage that you have here over having something where you would have to export your results to an individual mesh for an individual time step.
Oh, that is a great point. Yeah, thank you for that.
All right, so it looks like we are approaching about 10 minutes to the top of the hour, and questions have slowed down. So I think we will, if you don't have anything else, Sualp or Nelson, we may look at wrapping this up and giving some of our viewers some little bit of time back so they can get back to what they do.
Sounds good.
All right, well, thank you everyone for coming today to the Simulation IQ, Simulation Mechanical portion of the webinar series. And today we covered some information about the interoperability with Recurdyn and Simulation Mechanical. Sualp also went through some of the information regarding meshing parts in an assembly, as well as the availability of the Service Pack 1 that just came out recently. So I urge everybody to jump out there and get that downloaded and installed on their machines. And I think we'll go ahead and wrap things up, and we'll see you next time.